Good morning, everyone. This is our group reporting about the basic concepts of surveying. Surveying definition. Surveying is the science and art of making all essential measurements to determine the relative positions of points or physical and cultural details above, on, or beneath the surface of the earth, and to depict them in a usable form or to establish the positions of points or details. Civil surveying is an engineering operation that involves assessing and recording details about an area of land. These observations can then be used to help plan construction projects. The main purpose of surveying in civil engineering is to determine the three-dimensional relationship between different locations. These are the uses of surveying: creating topographical marine navigational maps, preparing tools, planning for new construction projects, estimating projected path of roads, railways, power lines, and irrigation system, assessing and recording the boundaries of different properties to determine land ownership, analyzing topography, assessing the position of existing creatures like highways, canals, dams, and bridges, planning and constructing mines, preparing for military operations and engagements, and charting navigational routes. Next is the types of surveying. First one is land surveying. Land surveying involves measuring and determining property boundaries. Property boundaries are the basis for all property transactions, including buying, selling, mortgaging, and leasing. Next is mining surveying. Mining surveying involves in planning, construction, and operation of various types of mines. These mines may be open, cut, or underground. Types of mines include coal, metalliferous, and mineral sands. Next is hydrographic surveying. Hydrographic surveying involves undertaking measurements under the surface of the sea, harbors, and rivers, and on the adjacent shores. Their measurements are used to prepare charts of waterways and the sea, for use by ships and boats to ensure a safe passage, and for the design of infrastructure such as docks and jetties on ports and harbors. Next is geodetic surveying. Geodetic surveying involved with undertaking very precise measurements to determine the shape and size of the world and track the movement of continents. Their measurements are used in the monitoring of sea level rise, earthquakes, and the tracking of satellites. Next one is topographic. Topographic is about defining the location and heights of any number and variety of features on a site. Topographical plans can show contours along with the physical features located. This type of survey is regularly used when designing for roads, buildings, extensions, and other new infrastructure. Next one is cadastral surveying. Cadastral surveying collects data relating to plots of land and update the data as necessary. This means it makes a valuable contribution towards the safeguarding of real estate. The results of cadastral surveys are recorded in the plan for the land register. City surveying. City surveying is considering all development works necessary for the city. The development works like street roads, property boundaries, water and sanitary pipes location, electrical lines, telephone lines, etc. are involved in the city surveying. Construction surveying. Construction surveying is used to establish the location and alignment of highways, bridges, buildings, pipes, and other man-made objects. After large-scale projects are completed, an as-built survey is performed to locate any modifications that were made to the plans during construction. Next is forest surveying. Forest surveying is to obtain information on the condition of the forest and monitor any changes, since there are not only surveys of standing trees but also surveys after logging as well as forestry surveys aimed at prescribing treatments. Next is industrial surveying. Industrial surveying could involve the oil and gas industry, mechanics, the process industry, power plants, etc. The projects may be large or small and of varying duration. ANCOS surveys often complement each other and are rarely isolated single services. Photogrammetric surveying is the branch of surveying in which maps are prepared from photographs taken from ground or air stations. Photogrammetry may employ high-speed imaging and remote sensing in order to detect, measure, and record complex 2D and 3D motion fields. And the last one is route surveying. For the location and construction of lines of transportation or communication that continue across the country for some distance, such as highways, railroads, open conduit systems, pipelines, and power or telecom lines. Surveying instrumentation. Automatic level. Automatic level is used to establish or verify points in the same horizontal plane. Engineering transit. It is used for measuring horizontal and vertical angles. Theodolite. Theodolite is used for precise angular measurement in both horizontal and vertical planes. Total station. Total station is useful for measuring horizontal angles, vertical angles, and distance. Steel tape. Steel tape is used in surveying to measure horizontal, vertical, and slope distances. Rangefinder. It is used to measure the distance from the instrument to a selected point or object. Plumb bob. Plumb bob is used to make sure that the construction are plumb, but it can be also used in surveying to establish the nadir with respect to gravity at a specific point. Leveling rod. Leveling rod is used to measure vertical distance, which is the difference in elevation between a line of sight and the required point above or below it. Range poles. It is used to mark areas and to set out straight lines in the field. They are also used to mark points which must be seen from a distance, in which case a flag may be attached to improve the visibility. Survey markers. Survey markers are used to mark specific locations, which can be done with a nail that permanently attaches it to the ground or surface.
I'm Helge Friedhuis, and in this section I'll be talking about care and handling of instrument. Surveying equipment tends to be fairly fragile. That is why it is critical to maintain them regularly to ensure accurate calibration, proper function, and to prevent future repairs or replacements. Use the carrying case for storage and transport. Now we should always remember that the level should always be kept in the box when not used. Now for transporting the surveying equipment, always properly place the land surveying instruments in storage cases before transporting. Now just because land surveying instruments are properly placed in storage cases, it does not mean that you can handle the case roughly. The case and instrument should never be dropped or impacted, because anytime you knock them around or drop them, they have a chance of getting knocked out of calibration, so it won't produce accurate results anymore. And for the handling of the surveying equipment in open spaces, the lever may be carried on the shoulder and preferably in a vertical position. The spindle should be clamped slightly so that the telescope does not rotate when carried, and it must be in full view of the person carrying it. This is to avoid hitting into trees and underbrush. And for the handling of the surveying equipment in densely forested areas, the level should be cradled between the arms and held close to one's left or right chest. And the spindle should be unclamped. This is to allow the telescope to turn freely and give away readily to any pressure or possible collision with an object. Surveying field notes. Surveying field notes constitute the only reliable and permanent record of actual work done in field. So field notes are prepared to record all pertinent information, measurements, calculations, sketches, and observations made by the surveyor during the course of the survey. In choosing field notebook, it should be of good quality rag paper with stiff board or leather cover made to withstand hard usage and of pocket size. So basically for the field notes you will need something sturdy, durable, and that can withstand numerous environmental elements, especially water. So there are 5 types of notes. First one is we have sketches and tabulations, and explanatory notes, computations, and combination of the above. So this picture right here is an example of a field note. Now in this section we are going to talk about the different positions and their duties of each member of the survey party. First up is we have the chief of party, which is the person who is responsible for the overall direction. This includes the supervision and operational control of the survey party. Next one is the assistant chief of party. This person assists the chief of party in the accomplishment of the task assigned to the survey party. Instrument man is the person who sets up, level, and operates surveying instruments such as the transit, engineer's level, theodolite, plane table, and etc. The technician is responsible for use and operation of all electronic instruments required in a fieldwork operation. The computer is the person who performs all computations of survey data and works out necessary computational checks required in a fieldwork operation. Recorder is the person who keeps a record of all sketches, drawings, measurements, and observations taken or needed for a fieldwork operation. The head tape man is the person responsible for the accuracy and speed of all linear measurements with tape. The rear tape man is the person who assists the head tape man during taping operations and in other related work. Flagman is the person holding the flagpole or range pole at selected points as directed by the instrument man during operation. The rodman, whose primary duty is to hold the stadia or levering rod when sights are to be taken on it. The pacer is the person who checks all linear measurements made by the tapeman. Axeman or lineman is the person whose duty is to clear the line of sight of trees, bush, and other obstructions in wooded country. Aidman is the person whose duty is to render first aid treatment to members of the survey party who are involved in cases involving their health, safety, and well-being. Lastly, the utility men are the persons whose duties are to render other forms of assistance needed by the survey party.
Accuracy of measurements. Direct versus indirect measurements. First is the direct measurements. The key word is direct, so this is a simple method in which the value of the quantity to be measured can be obtained directly without any calculations needed. So it is a quantity that can be measured directly, and the examples are weight and length. Next is the indirect measurements. In the indirect method of measurement, the value of the quantity to be measured is obtained by measuring other quantities which are functionally related to the required value. So it normally involves properties pertaining to trigonometry and geometry. An example would be using an instrument called a sine bar in order to measure the angle of an object in which it won't directly display its value. Units of measurement. First is the International System of Units, or the SI. It is the modern metric system of measurement and the dominant system of international commerce and trade. This system is also called the metric system. Units in SI of major concern to surveying are meter for the linear measure, square meter for areas, cubic meter for volumes, and radian for angles. Here on the next slide, we can see some common prefixes that are being used. Next would be linear, area, and volume measurements. The common units for length are kilometer, meter, centimeter, and millimeter. The unit of area in SI is the square meter. The following are the commonly used relationships. 1 hectare equals 10,000 square meters. 1 acre is equal to 100 square meters. 1 square kilometer is equal to 1 million square meters, and it would be equal to 100 hectares. The common metric units for volume are the cubic meter, liter, and milliliter. Lastly is the angular measurements. So the SI unit for plane angles is the radian. And we should also take note of the conversion between radian and degrees, which is 2 pi rad is equal to 360 degrees. In the Philippines, the sexagesimal units are used with SI because of their practical importance and our familiarity with it. So in the sexagesimal units, the angle is measured in degrees, minutes, and seconds. On the other hand, in the centesimal units, the angle is measured in grad. And note that the circumference of a circle is divided into 400 grads. Next is errors and mistakes. An error is inherent in all measurements and results from sources that cannot be avoided. It is also the difference between the true value and the measured value of a quantity. Mistakes, on the other hand, arise from inattention, inexperience, carelessness, and poor judgment or confusion in the mind of the observer. They do not follow any mathematical rule or the law of probability and may be large or small, positive or negative. Mistakes are also caused by misunderstanding of the problem, inexperience, and indifference of the surveyor. Mistakes that are frequently committed include reading the wrong graduation of the tape, transposition of figures, reading a scale backwards, misplacing a decimal point, and incorrect reading of field notes. Next is we will move on to the types of errors. So first is the systematic error. For systematic error, this will always have the same sign and magnitude as long as field conditions remain constant and unchanged. A systematic error always follows some definite mathematical or physical law, and correction can be determined and applied. It can also be called cumulative. So these errors may be eliminated by applying corrections, employing proper techniques in the use of instruments, and adopting a field procedure that automatically eliminates the error. Next is the accidental errors. Accidental errors are errors that occur due to unavoidable circumstances like variations in atmospheric conditions which are entirely beyond the control of the observer. Other causes for accidental errors would be due to imperfection in measuring instruments and imperfection of eyesight. So for accidental errors, it is beyond the control of the observer. Sources of errors. Sources of errors include instrumental errors, natural, and personal. Instrumental errors are due to imperfections in the instruments used, either from faults in their construction or improper adjustments between the different parts prior to their use. Natural errors are caused by variations in the phenomena of nature such as temperature, gravity, wind, humidity, the curvature of the earth, and refraction changes in magnetic declination. Personal errors arise from limitations of the senses of sight, touch, and hearing of the human observer, which are likely to be erroneous or inaccurate. Next, accuracy and precision. Accuracy refers to the level of agreement between the actual measurement and the absolute measurement. In other words, it indicates how close a given measurement is to the absolute or true value. Precision implies the level of variation that lies in the values of several measurements of the same factor. In simple words, it refers to how consistent the results are regardless of how close they are to the true value. The theory of probability. Probability is the number of times something will probably occur over the range of possible occurrences. The theory of probability is based upon the following assumptions relative to the occurrences of errors. Small errors occur more often than large ones, and that they are more probable. Large errors happen infrequently and are therefore less probable. For normally distributed errors, unusually large ones may be mistakes rather than accidental errors. Positive and negative errors of the same size happen with equal frequency, that is, they are equally probable. The mean of an infinite number of observations is the most probable value. Next is the most probable value, or MPV. It refers to the quantity which, based on available data, has more chances of being correct than any other. So if a given quantity is measured more than one time, not all the derived values are correct. There is only one correct value that should be considered, and it is determined by this following formula. MPV is equal to the mean, which is equal to the sum of all values divided by the number of values been given. So basically, to better understand the most probable value, it is the mean. You can call it the mean. So here we have a given problem set. A surveying instructor sent out 6 groups of students to measure a distance between 2 points marked on the ground. The students came up with the following 6 different values: 250.25, 250.15, 249.90, 251.04, 250.50, and 251.22 meters. Assuming that these values are equally reliable and that variations result from accidental errors, determine the most probable value of the distance measured. So we know that the most probable value is the mean. So we will use the formula of the mean. So we will first sum up the values given, and then divide it by the number of values available. So the summation of all of the values given is 1503.06 divided by the number of values, which is 6, and so the final answer would be 250.51 meters. So now we'll move on to the second sample problem. So the angles about a point Q have the following observed values: 130 degrees 15 minutes 20 seconds, 142 degrees 37 minutes 30 seconds, and 87 degrees 7 minutes 40 seconds. Determine the most probable value of each angle. So the first thing that we'll do is to illustrate the given problem. So here we now have a illustration of it. So as you can see in the illustration, it somehow forms into a circle, which means if you will sum up all of the given values, it should equate to 360 degrees. So the first thing we'll do is to sum up to check it. So here, sum up all the angles. Then as you can see in the final answer, it is 360 degrees and 30 seconds. So there's something wrong with it. So the next thing that we will do is to find the discrepancy. So the discrepancy is equal to the expected corrected sum minus the sum of the observed value. So our expected corrected sum is 360 degrees because it should be a circle, so it should be 360 degrees minus the our sum, our observed value. It would 360 degrees 30 seconds. So our answer is negative 30 seconds. And next is we will get the correction, and the correction is the discrepancy minus the number of values we have, which is 3. And so our correction would be negative 10 seconds. And next is we will uh, uh, determine the MPV of the angles, because we now have the correction. And so to determine it, we have the given formula, angle, our given angle plus the correction. So here the first angle, 142 degrees 37 minutes 30 seconds, plus our correction, which is negative 10 seconds. And so we have our final MPV, the 142 degrees 37 minutes 20 seconds. And for our uh, second angle, it would be 87 degrees 7 minutes 30 seconds. And for our final angle would be 130 degrees 15 minutes and 10 seconds. So these are the final answers na. Next is the relative precision. The total amount of error in a given measurement should relate to the magnitude of the measured quantity in order to indicate the accuracy of a measurement. So as shown below, it is expressed by a fraction having the magnitude of the error in the numerator and the magnitude of a measured quantity in the denominator. So for the probable error, which can be seen at the numerator of the relative precision formula, it is the quantity which, when added to and subtracted from the most probable value, defines a range within which there is a 50% chance that the true value of the measured quantity lies inside or outside of it. So given on the side is the formula for the probable error. Pe sub s is the probable error of any single measurement of a series. Pe sub m is the probable error of the mean. And summation v squared is the summation of the squares of the residual. And n is the number of observation. So for the residual, it is the difference between any measured value of a quantity and its most probable value. So the formula is given on the side, where v is the residual in any measurement, x is the measurement made of a particular quantity, and x bar is the most probable value of the quantity measured. Lastly is the weighted observations. So the weighted observations are the estimated degree of reliability or weight for each of the measurements before they are combined and the most probable values are determined. So here we have a sample problem for our weighted observations. 4 measurements of a distance were recorded as 284.18, 284.19, 284.22, and 284.20 meters, and given weights 1, 3, 2, and 4 respectively. Determine the weighted mean. So we will be using the formula for the weighted mean. So here, all the x sub i's denotes data points or the given values, while the w sub I denotes the weight. So the sum of the product of the all the weights and the data points divided by the sum of all the weights will give us the weighted mean. So plugging in all of the values, we get the final answer, 284.20 meters.
Measurement of distances. Measurement of distance. The accurate determination of the distance between the 2 points on any surface is one of the basic operations of plane surveying. In surveying, the distance between 2 points is understood to mean the horizontal distance, regardless of the relative elevation of the 2 points. There are several methods of determining distance. The choice depends on the purpose for which the measurement is intended and the required precision. In surveying, the most commonly employed methods of linear measurement include pacing, taping, tachymetric, graphical, mathematical, mechanical, photogrammetric, and the EDM or the electronic distance measurement. First is the distance by pacing. Pacing is the simplest and easiest method of measuring distance. Pacing consists of counting the numbers of steps or paces in a required distance. It also means moving with a measured steps. We all know pace is equals to one step and stride is equivalent to two paces, which is two steps. So here is a illustration of what I am talking in the previous slide. So to compute with the pace factor is equals to the length of the line over the mean number of paces. Distance by pacing. Pace factor. To pace a distance, the length of one's pace must first be determined because pace factor will be different for each individual and change with time. It is also important to walk naturally when calibrating one's pace and in pacing distances, and care should be taken to walk in a straight line. And it is a good idea to have a mechanical counter with you, such as a pedometer or a pasometer when pacing a long distance. So there are several factors that can cause variation in pace factors, such as the roughness of the road, speed of pacing, type of vegetation, slope of the ground, age and gender of the individual, and fatigue on the part of the pacer. Distance by tachymetry. Tachymetry is another procedure of obtaining horizontal distances. It is based on the optical geometry of the instrument employed, and it is an indirect method of measurement. A transit or a theodolite is used to determine the subtended intervals and angles on the graduated Rother scale, from which the distances are computed by trigonometry. And tachymetry measurements are done using either the stadia technique or the subtense bar method. Stadia method provides a rapid means of determining the horizontal distances. The precision of the stadia method depends on the refinement with which the instrument was manufactured, the skills of the observer, the length of the measurement effects of refraction and parallax. The equipment for stadia measurements consists of telescope with two horizontal hairs called stadia hairs and a graduated rod called stadia rod. The telescope of most surveying instruments are equipped with stadia hair, and when you look at to the telescope, this is what you see. The process of taking stadia measurements consists in observing through the telescope the apparent location of the two stadia hair on a vertically held rod. The distance from the telescope to the rod is found by the proportional relationship in similar triangles. So the equation is D is equals to KS plus C is employed in computing the horizontal distances from stadia intervals when sites are horizontal. So here is a illustration of what I am talking about in the previous slide. So the telescope, the horizontal, and the stadia rod. So if we are going to measure the distance between the telescope and the stadia rod using this formula, D is equals to Ks plus C, where D is the distance from the telescope to the rod. C is the stadia constant, distance from the center of the instrument to the principal focus. This is usually 0 for internal focusing telescope. And K is a stadia interval factor of the instrument, usually 100. And S is stadia interval, difference between the upper and lower hair. So to illustrate the formula from the previous slide, we are going to answer this. A stadia rod held at the distance point B is sighted by an instrument set up at A. The upper and the lower stadia hair readings were observed as 1.3 and 0.9 meters, respectively. If the stadia interval factor K is 100 and the instrument constant C is 0, determine the length of line AB. So we all know this formula. To get your distance from the telescope to the rod is Ks plus C. So we are going to substitute it. So K is equals to 100, and S, as we all know that it is a difference, 1.3 minus 0.9 meters plus 0. So your distance from your telescope to your rod is 40 meters. So next is the distance of tachymetry. First is the subtense bar method. The subtense bar method is a convenient and practical device used for quick and accurate measurement of horizontal distances. So the bar, which is precisely 2 meters long, consists of a rounded steel tube through which runs a thin in-bar rod. So, subtense bar method. The procedure for determining the distance between the points consists of first is setting up the subtense bar at the distance station. Second is measuring the horizontal angle subtended by the distance between two targets. Third is a theodolite set up at the other end of the line to be measured is used in measuring subtending angles. So the equation for the horizontal distance where your theodolite or transit is the point T to the subtense bar method. To get that distance is to use this equation, which is D is equals to cotangent alpha over 2. This is an illustrative problem. Example is the following subtense angles were read on a 2 meters long subtended bar using a theodolite of 0 degrees 54 minutes 13 seconds and a 0 degree 22 minutes 20 seconds. So compute each horizontal distance from the theodolite to each position of the bar. So this vertical line here is where your subtense bar, and the circle here is where your theodolite, and the line here is is the horizontal. Then D1 is your first equation, which is point A, and D2 is the equation of point B to this subtense bar. So D1 is equals to cotangent times 0 degree 54 minutes 13 seconds over 2. So which is 126.81 meters. Then your D2, to compute your D2, is cotangent times 0 degree 22 minutes 20 seconds over 2, which is 307.86 meters. To compute for the whole distance from point A to point B, you have to add the distance 1 and the distance 2, which is equivalent of 434.6 meters. Distance by graphical and mathematical methods. A known distance may be determined through the relationship with known distances geometrically. This method are widely employed in plane table surveys and in triangulation works. In inaccessible terrain, this method becomes quite practical to employ. Distance by mechanical devices. These devices are only applicable for low precision surveys or where quick measurements are desired. The more commonly used among these devices include the odometer, measuring wheel, and the optical rangefinder. So the odometer is simply device that can be attached to a wheel for purpose of roughly measuring surface distances. And the optical rangefinder, this device can be used to determine the distances approximately simply by focusing. So here is the distance by photogrammetry. Photogrammetry refers to a measurement of images on a photograph. So there are two general types of photogrammetry exist. The aerial is with the camera in the air, and the terrestrial with the camera handled on a tripod. With the terrestrial photogrammetry, dealing with the object distances up to 200 meters is also termed close-range photogrammetry. Distance by electronic distance measurement, or the EDM. This is a method of determining the length between 2 points using electromagnetic waves. The basic principle of electro-optical devices is the indirect determination of the time required for an electromagnetic radiation to travel between two stations. Distance by taping. Taping is the linear measurement of the horizontal distance between 2 points using a surveyor's tape. Direct measuring using a tape is the most common method of calculating distance. So the following condition which could exist during a taping operation. First is substandard lengths due to either faults in their manufacturer or damage on the tape, which causes by kinks, bends, cuts, and splices on the tapes. Second is ends of the tape are not held at the same level when breaking tape along inclined or rough terrain surface or when undertaking slope taping. Third is inaccuracy in keeping the tape along the straight line during the measurement or in laying out of the lengths. Then here is a continuation. The tape is not of nominal length due to the difference in the temperature prevailing during the actual measurement. Next is the shortening or lengthening of the tape due to the application of pull applied on the tape during the standardization. And lastly, the distance between the end of the points of unsupported length of tape is less than the specified nominal length due to the effect of a sag or a strong blowing side wind. So, the procedure of taping. First is aligning the tape. So, in aligning the tape, when a line is to be measured, both ends must be marked. It may also be necessary to establish a few intermediate points to serve as guides in obtaining a straight line. So second is stretching the tape. A steady and firm pull, generally between 4 and 7 kg, is applied on one end of the tape during stretching. Remember, no measurement should be made without stretching the tape since tapes are correct in length only when a standard pull is applied to it. And third is the plumbing. Both ends of the tape should be held above the ground, about the level of the waist or chest, and in horizontal position. Also, each end of the tape is marked by positioning plumbing line. Fourth is marking full tape length. When a length when a full tape length is measured, the rear tape man holds his end of the tape opposite the pin earlier set on the ground. The head of a tape man, after being lined in properly, exerts the required pull on the tape, notes the zero end, and sets a pin beside it. And fifth is the tallying tape measurement. At the initial point, the rear tape man holds one pin and the head tape man begins on 10 pins carried on his steel rings. This is the reason why a set of 11 pin is normally used during taping operation. Sixth is measuring fractional length. When last segment of line is to be measured, this will often be a measurement which will consist of a fractional tape length. Tape correction due to pull. During a calibration or standardization, a tape is subjected to a certain amount of standard pull or tension on its end. The tape stretches in an elastic manner, and since the modulus of elasticity of a material can be expressed as a ratio of unit stress to unit elongation, the change in length can be determined in this equation. Unit stress over elongation is equals to P over A over E over L. So where CP is the total elongation and tape length due to pull of the correction due to incorrect pull applied on the tape. That is meters. So PM pulled applied to the tape during measurement. P as standard for the tape or pull for which the tape is calibrated. And L measured length of the line. And A cross-sectional area of the tape. E is the modulus of elasticity of the tape material. L is the corrected length of the measured line. Tape correction due to temperature. The tape lengthens as the temperature rises and shortens as the temperature falls. The correction applied to the length of the tape due to the change in temperature Ct is given by the formula. So correction due to temperature is equals to C, where coefficient of linear expansion times L, the length of the tape, times the T minus Ts, where T is the observed temperature of the tape at the time of the measurement and Ts is the temperature at which the tape was standardized. So, tape correction due to sag. The correction for sag is equals to the difference in length between the arc and its subtended chord and is always negative. As the sag correction is a function of the weight of the tape, it will be greater for heavy tapes than light ones. A tape not supported along its length will sag and form a catenary between end supports. The correction due to sag must be calculated separately for each unsupported strength separately and is given by the equation of Cs is equals to omega squared L L cubed over 24p squared, and is derived to CS is equals to W squared L over 24p squared. So omega is weight of the tape per unit length, and W is the total weight of the tape between supports, and P is the tension or pull applied on the tape. So, tape correction due to slope. So when distance are measured along the slope, the equivalent horizontal distance may be determined by applying a slope correction. So this is the equation for the correction due to slope. Correction due to slope is equals to h squared over s plus d, where h is the height of the slope, d is the horizontal distance, s is the slope distance measured between the 2 points on the slope line. And lastly, the combined tape correction. We all know that in surveying, tape correction refers to correcting measurements for the effect of slope, angle, expansion, or contraction due to temperature, and the tape sag, which varies with the applied tension. Not correcting for these effects gives rise to symmetric errors, etc., effects which act in a predictable manner and therefore can be corrected by mathematical methods. So here are the equations from the previous slide. The correction for the effects of incorrect length of tape, temperature, tension, slope, and sag may be combined as a single net correction per tape length.